A philosopher named Bertrand Russell once said that the problem is that fools and fanatics are always so certain of themselves and wiser people so full of doubts. There was a study that showed that the more you know, the less you think you know, but the less someone knows about a particular subject, the more likely they'd act like they knew more than all the best educated expert specialists anywhere ever. It's called the Dunning-Kruger effect, but this phenomenon was known a long time before that study. In the 1800s, naturalist Charles Darwin remarked that ignorance more frequently begets confidence than does knowledge. It's okay to be confident, but only as long as you can back it up. There is such a thing as reasonable certainty, but you have to be careful not to be fooled either by misinformation or your own biases. There has to be some way to know what is really true and how true it is. This is why scientists rely on evidence for everything. They say that positive claims require positive evidence. Extraordinary claims require extraordinary evidence, and what can be asserted without evidence can be dismissed without evidence. They're very careful not to say that something is a fact unless it is evidently true, because if a scientist turns out to be wrong, or says something is definitely true when they can't show that it is, that'll hurt his or her credibility. They can't just say that anything is possible either, not without some evident precedent or parallel showing whether it is possible, or when the evidence indicates that to be the case, regardless whether they can yet explain that or not. Accuracy and accountability matter. So everything a scientist says is going to be checked by other scientists who are looking for mistakes. It's called the process of peer review. It is continuous, relentless, and unforgiving. So scientists are very careful to distinguish whatever they might believe from what they actually know. And they're still hesitant to say that they know things, even when they do. Because in science, knowledge is a justified belief, meaning that it has measurable accuracy. You can be tested on your knowledge to show what you know. But if you can't demonstrate that knowledge to any degree at all, by any means whatsoever, then how could you be sure whether you understand or remember everything correctly? Sometimes you'll hear two people arguing, and both of them might say that, I know for a fact that I'm right, even when they can't both be right at the same time. If they're arguing a matter of fact, then one of them should be able to prove it. A fact is just a point of data that is either not a dispute or is indisputable because it can be verified objectively. In some cases, you can just look it up to show who's right. But if there's no way anyone could ever verify it, then there's no way to be sure if we know it either. If they can show the facts of the matter, then one of them might say, that doesn't prove anything. We both got the same evidence, we're just interpreting it differently. But that can't be right either, because the evidence has to be factual. Two different explanations could account for the same fact, even if they're otherwise completely opposite. But the same fact can't be evidence of both conclusions, because in order to qualify as evidence, the fact should only indicate one available option over any other. Now, what if you're arguing about something that you can't look up, because no one knows the answer? Science may still have a way to figure that out. Make a couple of guesses as to what the answer might be. Maybe this is the reason, or maybe this happens because of that. Whatever your explanation is, there should be a way to test it. That would be your hypothesis, and you can test it with an experiment. Even if you couldn't possibly guess what the explanation is, you can still experiment to figure it out. If you don't have a clue, experiments could provide one. For example, Sir Isaac Newton famously discovered gravity. Why is that such a great thing? Obviously, everybody already knew that things fall down, right? He wasn't the first to discover that. In fact, Galileo had already performed a series of experiments to show that a bowling ball and a tennis ball will fall at exactly the same speed if you drop them together, assuming there's no wind, of course. They'll also accelerate at the same rate when rolling downhill. These are simple experiments Galileo did to try to figure out how things fall. Newton was the first to ponder the reason why things fall. Seems no one had ever explained that before. He proposed that the reason things fall down was because of gravity, a hypothetical physical force connected to mass, that an apple falls to the earth because matter attracts matter. But you know what? That was like 300 years ago, and we still don't know exactly why matter attracts matter. That's why we built super colliders to perform more experiments and test new hypotheses. The idea that matter attracts matter is one of the laws of nature. Natural laws are merely observations people made which can be expressed as a sentence or a mathematical equation, and Newton provided several of each. The laws of nature are general statements which are always correct under particular circumstances. And a lot of people confuse the theory of gravity with the law of gravity, and that might be because Newton based his entire theory on an erroneous law, that the gravitational force of massive bodies is directly proportional to the product of their mass and inversely proportional to the square of the distance between them. That seemed to be correct. It even explains the motions of the planets once you figure in their inertia. Well, most of the planets anyway. It turned out that Newton's law of the inverse square failed to account for certain peculiarities in the orbit of the planet Mercury. So the law of gravity was wrong. Newton didn't know everything. Fortunately, another scientist stepped in to re-establish gravity before anyone floated away into space. Albert Einstein's general theory of relativity does account for the peculiarities in the planet Mercury, and a number of other things too. At present, the theory of relativity is the best representation of the theory of gravity. So the fact of gravity is that things fall down. The laws of gravity say how things fall down, but the theory of gravity explains why things fall down, the forces, catalysts, or mechanics behind it. And people often confuse these words, and that's not surprising. The way science defines the word theory has changed over the last couple hundred years. Hypotheses and theories are not the same thing. You can't prove a theory and have it become a law either. Theories aren't supposed to be proven at all, though there are a couple of exceptions. Einstein's theory of relativity was proven a few times, and Louis Pasteur's germ theory of disease was effectively proven too. We know that germs are real, and they've been proven to cause diseases. Same with atomic theory. We can prove that atoms are real too. Much of biology is based on cell theory. All of these are facts that have laws associated with them, yet we still call each of these theory. In science, a theory is like a field of study. Some of you may have taken classes in music theory, and if you have, then you know what I mean. Can you prove music theory? A scientific theory is a body of knowledge, including the facts, hypotheses, and natural laws pertaining to a particular subject, in an attempt to explain some aspect of nature. The rule is that theories are not to be proved, but they can be disproved. And science has disproved a few theories in the past. However, that's not likely to happen anymore because most modern scientific theories have already been validated by critical analysis, having endured rigorous testing and peer review, and they've been repeatedly confirmed by evidence and experiments. So the most that happens now is that theories may change in accordance with new information. All of this is so that scientists won't pretend to know what they don't really know, and to be sure that whatever we do know is verifiably accurate. Science is a self-correcting process that works like a game of 20 questions, where each new discovery gives us a better, more complete, or more precise idea of what the truth really is. We don't know everything about everything. We don't know everything about anything. And the only way to improve our understanding is to seek out the flaws in our current perception and correct them.